Okay, welcome. So we are discussing about hardware synchronization under process synchronization. So in the last lecture we have discussed about test and set instruction, which is an atomic hardware instruction to overcome the problem of critical section. So in today's class we will be discussing a similar instruction which is used to achieve hardware based process synchronization, and that instruction is called as compare and swap instruction. So first let us understand how this instruction works. So this compare and swap instruction, so basically is a function, but it executes as a one single unit. That is, it will execute as an atomic instruction, that once it is called, then all these instructions will execute. Then only the context switch will in between. There will not be any context switch, that will be ensured. So these instructions will execute in atomic way. Okay, and if you see this particular function compare and set, it returns a value of type integer, and it takes three arguments. One is a pointer, one is a pointer to an integer, and two other integer values. One is expected, the other one is new value. Okay, so we have a pointer value. Okay, and this value, it is pointing to some memory location which holds an integer value, so we don't know what is its value. So basically it holds the value of the lock. So lock can be either true or false. As it is integer, it can be either 1 or 0. So basically the pointer value points to an address, and that memory location can contain either 0 or 1. Okay, and the function, what it does in the sense, this atomic instruction, what it does in the sense, it sets temp equal to star value. So as already stated, star represents value at address. Okay, so here star represents declaration, here pointer is declared. Okay, and also if the function is called, then the address will be assigned to the pointer. Okay, so that the pointer will point to the address. But in normal programming instruction, wherever star comes, you have to read it as value at. So here you have to read at value at uh, this particular, the value at the address pointed by value. Similarly, this is value at the address pointed by value. Similarly, this is also value at the address pointed by value. Okay. So first what we are doing, temp is equal to star value. So there is a temporary variable of type integer, and that will be holding the value what, star value. So star represents value at the location pointed by value. So value is pointing this particular memory location, and that location contains either 0 or 1. So we don't know currently what it is. So whatever it is, that will be stored in temp. So if value contains 0, then temp will also hold 0. If value contains 1, then temp will also hold 1. Okay, then what we check is if star value is equal to expected. If star value is equal to expected means what? Here expected in the sense, see, this expected will be always 0. Is expected, the value for the expected will be always 0, and new value will be always 1. So that is, if a process want to enter into a critical section, what it expects, if a process P1 want to enter a critical section, what it expects? It expects that currently nobody should be in the critical section. Okay, so that is, it expects that currently the lock is 0. Currently that lock should be 0, so that P1 can enter into critical section. If a process P1 want to enter the critical section, what it expects? It expects lock to be 0 so that it can enter. If lock is 1, it cannot enter. So this expected value, whenever this compare and swap is being called, the expected value will be passed a value 0. Okay, and the new value will be always 1. Okay, because if if P1 want to access the critical section, and if lock is 0, then P1 will be allowed to enter critical section. But before entering the critical section, what P1 should do? P1 should make lock equal to 1. Okay, so that new value is always 1. So here the instruction will be something like L lock is equal to new value. Okay, because previously uh, P1 want to enter the critical section and it expects lock to be 0. If it is 0, it will enter. If it enter, then immediately lock should be made as 1. So that 1 is where it is stored, in the sense it will be stored in the new value. Okay. So 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 with this, what you should understand, in the sense expected will be always 0 and new value will be always 1. So the next if condition, it checks whether star value is equal to expected. So star value represents value at the location pointed by value. So value at this location can be either 0 or 1. You cannot, but this expected will be always 0. Okay. So let us consider both the cases. Let us consider one by one case. Currently, initially, let us assume value as 0. Okay, that is star value, that is the value is a pointer. Okay, the value at the location pointed by value is 0. Okay, then obviously what will be temp will also be 0. Okay, temp will also be 0. Okay, it means what? So this value, whatever the value here it is stored, it is nothing but it is the value of the lock. It means currently it is not locked. So this if condition checks if star value is equal to expected. What is star value? Value at the location pointed by value. That is 0. Is it equal to the expected value? Yes. Expected is that lock should be 0. It is 0. So both matched. So then star value is equal to new value. So now the value at the location pointed by value. Star represents value at location pointed by value. That will become new value. What is new value? New value is 1. Okay. New value is 1. So no more this is 0. No more this is 0. Now this has become 1. Okay. And return temp. Return temp. What is temp? Temp is 0. So return temp. So it will return the value of temp. What is temp? Temp is 0. Okay. So basically 0 will be returned. Okay. So 0 will be returned if the star value is 0. When you are calling compare and swap, if star value is 0, then 0 will be returned, but value will be made to 1. Okay. Now let us see the second case. Assume the compare and swap function is called with the value 0 for star value. Okay. So that is now, sorry, with the value 1, that is now the lock is on. That is somebody else is in the critical section. So now what will be temp equal to star value. So that is temp will be equal to 1. So in this case temp will be 1. In this case temp will be 1. And then it checks whether star value is equal to expected. Star value is value at the location pointed by value, that is 1. Is it equal to expected? No, it is not equal to expected. So this statement won't execute. So star value won't change. Star value will be 1 only. And return temp. What is temp? Temp is also 1. So it will return 1. 1 means what? Somebody is already using the critical section, so you wait. You don't enter the critical section. That is the meaning. Okay. And critical section is also 1. But previously it returns 0. If star value is called with 0, it returns 0. It means nobody is in the critical section and you can enter the critical section. Okay. So basically this is the idea. So this is what this particular compare and swap atomic instruction does. Okay. Now let us see how this can be get called. So it executes atomically and it returns the original value of the paused parameter value. Okay, whatever being paused to value, that it returns. But whether this part executes or not, that depends on the original value of star value. Okay, original value that is pointed by value. If that is 0, then this will execute. Otherwise, it won't execute. Okay. Okay. So initially, so there are two cases as I already said, but initially lock will be 0. Okay. So if lock is 0, okay, so this is how that particular function will be called. So here we have an do while loop which repeats for infinite number of times. Then we are using a while loop, and through this while loop we are calling compare and swap, and we are passing the address of lock. So lock is a shared variable which is shared among two processes which want to execute concurrently. Okay. So now lock can contain either 0 or 1, but it is initialized to 0. So let us start with 0th case. Okay. So if this address is 2000, if this address is 2000, then this address is paused. Then this address is paused. And the other two values paused are 0 and 1. Okay. So as long as this compare and swap does not return 0, okay, if it returns 0, then it will break the while loop. If it not returns 0, then it will keep on checking, keep on calling compare and swap by passing log and 0 and 1. Okay, so this is a, again this is a the while loop does not contain any statement, so it keep on rotates as long as the compare and swap not returns 0. The moment it returns 0, it will come out. Okay, so let us assume if lock is 0. So if lock is 0, then what happens? This address is paused. 2000 is paused. Here 2000 is paused. Okay, the address 2000 is paused for lock, and the other values are 0 and 1. So now 2000 is received in star value. Okay, what is star value? Star value is a pointer. So that means value is going to point the location. That means value is going to point the location 2000. Value is going to point the location 2000. Okay, so value is going to point the location whose address is 2000. This address is nothing but what? Lock. This address is nothing but lock. What lock contains? 0. So the value at this location is 0. And the other two values that is passed were 0 and 1. So 0 will be received in expected, and 1 will be received in new value. Okay. So rest of the things are whatever we already discussed. And now temp is equal to star value. That is, star value is value at this location. So temp will be equal to 1. So temp will be equal to 0, because star value is 0. So temp will be equal to 0. If star value is equal to expected, so what is value at star value is value at this location. What is the value at this location? 0. What is expected? 0. Yes, both are 0. It is matching. So then star value is equal to new value. What is new value? 1. So no, so now star value is value at this location. So now this will become 1. This will become 1, but it returns temp. What is temp? Temp is 0. So it will return 0. It will return 0. Okay. So here, coming back here, so basically this entire function we are calling, so now it has returned 0. So this while loop will continue only if it is not 0. As it is 0, it will come out of the while loop. So this 0 means what? This is the value of the lock, which, so it is confirmed that, so the compare and swap actually what it does in the sense, it compared, it checked whether the current lock is 0 or not. Lock is 0 means nobody is using the lock. Okay, and also it did one more thing. It made the value star value to 1. Star value is nothing but lock. So it currently, after checking, so after ensuring that currently nobody is in the critical section, that is lock is 0, after ensuring that, it made lock to 1. It made lock to 1. Why it made lock to 1? Because this process want to enter the critical section. So now as it returns 0, it breaks. So now it enters the critical section, it executes the critical section, and then it made lock to 0 and it comes out of the critical section. Okay. So this is the whole idea. If lock is 1, then what will happen? If lock is 1, then again the same address will be passed, but the lock value is now 1. Now the lock value is 1. So value is pointing to lock. So that is also 1. Now temp is equal to star value. What is star value? Value at location pointed by value. That is not 0, it is 1. Now if star value is equal to expected, what is star value now? Star value is not 0, it is 1. But what is expected? Expected is 0. So is both are same? No, it's not same. So this statement won't execute. Return temp. What is temp? Temp is 1. So it will return 1. So 1 means what? Currently the lock is on. It means somebody else is in the critical section. So in this case, this compare and swap, it returned 1. So 1 is not equal to 0. So it will keep on, which is true. 1 is not equal to 0 is true. So it will keep on spin here. So that is this process. Now it won't enter into the critical section. Okay. So this is how the compare and swap instruction works. And this is how it ensures that concurrency is achieved. Okay. So this is also hardware based synchronization where the compare and swap is executed as one single atomic instruction. Okay. Fine. So we have discussed two instructions based on what you call hardware synchronization, test and set and compare and swap. But the drawback with these instructions is that it is basically designed for only two processes, this compare and swap and test and set. It satisfies two conditions of what you call it. It satisfies the two conditions of the solution for critical section problem. That is, it satisfied the condition of mutual exclusion and also progress. That is, it ensures mutual exclusion. That is, if one process is in the critical section, then other process will not be in the critical section. And also it ensures progress. That is, no process will be waiting indefinitely to enter into critical section. Okay. And the third condition is bounded wait. It does not ensure bounded wait for more than one process, for more than two processes. Okay. If more than two processes were there, then the bounded wait is actually, it is not guaranteed here. Okay. So that is the drawback with these particular algorithms. So the next algorithm we'll be discussing is an improved version of test and wait. This is an improved version of test and wait with bounded waiting condition satisfied. Okay. So bounded waiting means what? If n processes are waiting to enter the critical section, and if currently the first process enters the critical section and it comes out, and then again it should enter only after n minus 1 process entered the critical section. Okay, all the remaining n minus 1 process should enter the critical section. Then only this first process should be once again allowed to enter the critical section. So this particular algorithm, this is which is an improved version of test and set. It ensures that. Okay. So let us try to understand this particular algorithm. It's a very interesting algorithm. So here we are maintaining an array, which is called as waiting. So this array can hold n number of processes. It can hold the status of n number of processes. So this array, waiting array, and this variable key. Okay, these are this waiting array is a shared variable. Okay, this waiting array is a shared variable. Okay, and lock is also a shared variable. Lock is also a shared variable. So what it does in the sense, it first makes, so let us consider this as a case for process I. If process I wants to enter the critical section, so here there are two shared variables. One is the array waiting array and the other one is the lock. Okay. If process I wants to enter the critical section, then what process I will do in the sense, it will make waiting of I is equal to true. That is, I'm waiting to enter the critical section. That is what it means. Okay. Then it also makes key equal to true. Then it also makes key equal to true. So basically here key represents, it is an assumption about lock. Okay, key represents, it is an assumption about lock. What is the current lock value? What is the current lock status? Whether the critical section is currently locked or not. Okay, so this is an assumption about a lock. This is not the current original value of the lock. It is an assumption about the lock. So key is assigned to true. That means the process PI is thinking that currently somebody is using the critical section. Okay. So So what I said is key is an assumption about the lock and key is assigned with true. It means that the process PA is currently assuming that somebody is using the critical section. Okay. So with that assumption, it is running this while loop while waiting of I and key. So waiting of I is true. Okay. Because PI is waiting, process PI is waiting. Okay. And it already made waiting of I is true. And key is also true because initially it assumes that somebody else is in the critical section. So that it set key as true. Okay, with this assumption, then now it calls test and set. Now it calls test and set with lock. Now it calls test and set with lock. Okay. Now you recall what the test and set algorithm will do. So here it is passing the actual lock. Here it is passing the actual lock. So if the actual lock is if the actual lock is false, okay, that is if the actual lock is false. False means what? Nobody is in the critical section. If the actual lock is false, then what test and set will do? It's the original or test and set logic. Okay. If the actual value is false, then test and set what it will do is target is received. Target is uh, target is a pointer. Okay. So that is pointing to some address. That is pointing to some address. Okay. So and that address contains what? That address contains false. Okay. So if you go back here and refer, here you are passing address of lock. Okay. So it means, and we are assuming lock contains false. So this is lock. This is lock. This is lock. And let us assume lock contains false. And say this address is 2000. This address is 2000. And it contains false. So this address 2000 is being paused. So here when you say address ampersand log, it means 2000 is paused there for uh, whatever the variable that is being used by the test and set. Okay. So here 2000 target is now pointing to the location 2000. 2000 is nothing but lock. 2000 is nothing but actually 2000 is nothing but the particular location which contains the lock. And what it contains? It contains false. It contains false. Okay. So now this algorithm, what it will do? RV is equal to star target. So RV will be star target is value at target. That is what? False. It will make it false. Okay. And then star target equal to true. Star target is value at target. Value at target is nothing but lock. Now it locks it. Because this process PI now want to enter as it is originally false. As the lock is originally false, that means nobody is using the lock. So I can enter and I made it true because I'm going to use it. And return RV. What is RV? False. So false is returned. Okay. So false is returned. So that false will be, sorry. So false will be returned. So that false, so key will be now holding the value false. Key will be now holding the value false. So now again it goes back and check. Waiting of I is true, but key is false. Key is false means what? Key is nothing but an assumption about lock. So it means that currently nobody is in the critical section, so I can enter the critical section. And already, but lock is set to true because process PI entered the critical section. Okay. So this is how it works when uh, when lock is false. If lock is true, it will just keep on wait. If lock is true, this test and set will return true, and as long as it does not becomes false, it will keep on wait. Nothing else will happen. Okay. Okay. Now coming to the following statement. So now this particular process PI, it it has broken the while loop and it has came in. So the moment it came in, already a key is false, then it is making waiting of I also as false. It means no more I am waiting. I already entered the critical section. Now, as you know, the lock and set instruction, I mean the test and set instruction has already made lock as 1. After making it 1 only, it is sending that target value which is 0. Okay. So then it executes the critical section part. Then it executes the critical section part. Okay. After executing the critical section part, what this algorithm does in the sense, say, let us assume a simple case. Let us assume P1, P2, P3, P4. These four processes are waiting for critical section. So let us assume currently P1 is in the critical section. So P1 executes critical section. Now after that, the critical section should be given to whom? Three processes are waiting, P2, P3, P4, and in this order they are waiting. So if you want to ensure uh, bounded waiting, then the critical section should be given to P2. So after executing critical section Pi, that is currently P1, what it is doing in the sense, j equal to I plus 1 modulo n. I is currently 1, I plus 1 is 2, 2 modulo n, 2 modulo n. Okay, so n is nothing but here 4. Okay, so n is 4. So or you can number this, instead of p1 to p3, you can number p0, p1, p2 and p3, so that this logic will work correctly. Okay, because here it is modulo thing is coming. So yeah, 1 minute. So this is p naught. So current process is p naught, next is p1, next is p2, next is p3. So I is p naught. So 0 plus 1, 0 plus 1 is 1, and number of process is 4. Total number of process is 4. So 1 modulo 4, what you will get is 1. So the next, so j will be 1. So j will be 1. Okay, so then it checks, while j not equal to I is 0, I is 0. Okay, so j is not equal to I, because j is 1 and I is 0. This is true. And waiting of j, yes, j is waiting, because it is enter, it want to enter the critical section, means obviously it will be waiting in its code. Okay, so for this is, we assume for pi. Similarly for pj, this will be waiting of j will be equal to true. So waiting of j will be true if these conditions are satisfied. Okay, so if these conditions, so while j of I not equal to I, and waiting of j. Okay, so then and not waiting of j, this is not waiting of j and not waiting of j. Okay, but in our case it is waiting, p1 is waiting. Okay, if it is not waiting, it will increment. Again j will increment, because as long as somebody is waiting, it will keep on increment. If it is not increment, if it is not waiting, it will come out. So in our case, p1 is waiting to enter the critical section, so it will come out. After coming out, it checks whether j equal to I or not. Why it is checking j equal to I? In the sense, assume that nobody is waiting after p0, p1 is not waiting, p2 is not waiting, p3 is not waiting, then the cycle will continue and it will come back to p0. Okay, then the cycle will continue and it will come back to P naught. But P naught just now only finished the critical section. So that we are checking this condition if j equal to I. If j is equal to I, then we are making lock equal to false. That means I don't want the critical section, like that it will come out. Okay. But if j is not equal to I, in our case, j is not equal to I. J is 1 and I is 0. Then what it does, waiting of j is equal to false. Okay, the moment you make waiting of j as false, okay, the moment you make waiting of j as false, then what will happen? Waiting of j is made as so in the jth process, this statement will be waiting, right? So waiting of j is false. Whatever the, irrespective of whatever the value of key, so key will be true only. Okay, key will be, previously it was true because I has not yet made it false, but still it will enter into the critical section. Still it will enter into the critical section, and and okay, still it will enter into the critical section, because this statement fails. So again waiting of j will be made as false and it will execute the critical section. Okay, so this logic basically it ensures that the bounded wait condition is satisfied. Okay, so that's it about today's session. So we have discussed basically three algorithms for hardware synchronization. One is test and set, the other one is compare and swap, and the other one is test and set with bounded waiting. Thank you.